Hey guys, it's just a quick video where I'm going to run through a practice test 1. So test 1, we're going to have 14 questions and you're going to have 2 hours and 30 minutes to do them. So let's do a quick little bit of a calculation here. We've got 2 times 60 plus 30. There you go. Divide 14. And so it turns out that we've got a little bit over 10 minutes per question. So about 10 minutes per question to get going. Now, so it's always worth having that in the back of your mind. So I'm going to skip to the second half of the test. So just to let you know, sort of the first half of the test, or there's going to be 7 questions. You're going to be presented with the questions in random order, but I've organized it here. 7 of the questions will be concerning the chapter 1 material, and then 7 of the questions will be concerning the week 2 material about gases. So I'm going to begin with the stuff about gases. So these questions may or may not have a familiar tone to them. So this question says a 10-litre tank at 7.62 degrees Celsius is filled with 10.5 grams of carbon dioxide gas and 19.5 grams of chlorine pentafluoride gas. You can assume both gases behave as ideal gases under these conditions. Calculate the total pressure in the tank. So what we know is that the relationship between pressure, volume, amount, and temperature is given by the ideal gas law. We want to calculate the total pressure, which will be P. So that's just going to be nRT on V. So we do have the temperature, 7.62 degrees Celsius. We have the volume, 10 litres. And what we need is the number of moles of gas there. And then we know that this guy is the ideal gas constant. So I need to get the number of moles of gas, and there's 2 components here, but we know that it doesn't matter that there's 2 components. It just depends not on the identity of the gas, but just on the total moles. So what we're going to do here is the number of moles of CO2 plus the number of moles of chlorine pentafluoride. That'll give us our total moles. So I'm going to go ahead and calculate that. So I'm going to need some molar masses. So for CO2, I've got 10.5 grams of CO2, and 1 mole of CO2 weighs however many grams. And then I'm going to need the same 19.5 grams of ClF5, and we'll need the molar mass of ClF5. Okay, so what I like to do is use one of these online molecular weight calculators. There's many of them. This is going to do a much better job than Googling the formulas. The first result in Google will often be, or sometimes be incorrect. I wouldn't say often. So 130.45, and I already know this one, 44.01. Okay, so put all of that into my calculator and I can get my total moles. So 10.5 times 1 on 44.01 plus 19.5 on 130.45. There we go. And I got 0.38806 moles total. Okay, there we go. Alright, so now there's really only one thing left to do before I can start plugging numbers in, and that's to convert this temperature to Kelvin by adding 273.15 to it. So we can go ahead and do that. So 7.62 plus 273.15. We go 280.77 Kelvin. So at this point, I'm ready to go, right? So my pressure equals my number of moles, 0.38806. Let's put the units in. Moles times my ideal gas constant, 0.0821, and that is liters, atmospheres per mole per Kelvin, and the units on that guy, and then times by my temperature in Kelvin, 280.77 Kelvin. Then we've got to divide that by my volume, which was 10 liters. Alright, so everything's in, always double check everything. 10 liters, 7.62, 10, yeah, okay, looks good. 3 sig figs. So what you can see here is it was 3 sig figs, so I carried through an extra couple of digits at each point, and then that way there's not going to be any mistakes. Just check my units. Moles cancels out, Kelvin cancels out, Kelvin cancels out, liters cancel out, liters cancel out. All that's left is ATM, which are good units for a pressure. Okay. So let's do it. So I got my 280.77. I've got to times that by 0.0821 and times that by 0.38806, and then I got to divide that by 10. So I know that it's about 20 liters. Yeah. Okay, let's just, I won't make any comment on that, but this is, I think, going to be around 1. Yeah. Okay. So here we go. So 0.894. So what I was going to say, I'll explain now, is that 1 mole of gas at sort of ordinary pressures has a volume of about 20 liters. So, you know, at ordinary temperatures. So this is sort of like 0.4 of a mole at 10 liters tells me I'm around ordinary atmospheric pressure, is what I was thinking here. So this was good. That's 3 sig figs. Just check my units. We're okay with ATM. We are, so we're good to go. All right, so I'm happy with that one, and I was well under my 10 minutes. All right, so this is definitely like a little unusual, and it might take you back to see this. And this question is asking us to calculate mole fractions and partial pressures in a mixture, and also the total pressure that's in a mixture of gases. And so we have to remember a couple of things. So the mole fraction of species A will be the moles of A over the total number of moles, and that number is always less than 1. Okay, so that's a little formula there for the mole fraction. So that's what's going to allow you to calculate these two things. And then the partial pressure of, say, component A is just equal to its mole fraction multiplied by the total pressure. That's a relationship worth having. So, you know, the total pressure is 1 atmosphere and half of your moles are A, and then the pressure of A would be 1/2. Okay, and then the final one, the total pressure here, this is our Dalton's law of total pressures. The pressure total is this equal to the sum of all of the pressures of the components. So they're kind of like the tools, if you will, that we're going to use for this. And remember that any particular partial pressure is always going to be less than the total pressure. So this number at the bottom is always going to be bigger than these two numbers up here. And then those two numbers there are going to always sum to the one that's at the bottom there. So, you know, the gases just behave as though they were the only gas in the container. So it says we have a 10-litre tank at 6.33 degrees Celsius filled with 11.5 grams of dinitrogen monoxide, so N2O, and 17.8 grams of sulfur tetrafluoride. Okay, so SF4. You can assume both gases behave as ideal gases under these conditions. calculate the mole fraction and partial pressure of each gas. So there's a couple of ways that you can do this, and probably the first thing is that you're not going to get out of calculating the moles of each one. So what I'm going to do is tackle it like this. Now remember, in a mixture of gases, each gas behaves as though it was the only gas present. So what I'm going to do is I'm going to do similar to what I did before. So I'm going to calculate the pressure of the N2O, which is just going to, via the ideal gas law, so PV equals nRT. So the pressure of N2O will be nRT on V, okay? And so then I'm also going to calculate, in the same way, I'm going to calculate the pressure of the SF4. So the pressure of the SF4 will be the number of moles of SF4, the volume, and then I'm going to add those two together, and I'm going to get the total pressure, okay? And that would be valid. Once I've got that bit, I'm going to work on this mole fraction stuff, okay? So that won't be too difficult. All right, so let's go ahead. We're going to need the number of moles of N2O, and so that's going to be my mass of N2O, which was 11.5 grams. And then I'm going to multiply that by 1 on the molar mass. So 1 mole of N2O has however many grams of N2O. So go over to my handy dandy molecular weight calculator, and here we go, N2O, and we're going to calculate 44.01. We saw that number before, didn't we? So grams cancel that, and I know I got it. Alright, so 11.5 times 1 over 44.01 enter, and 0.26130. We're going to go to 3 sig figs. So if I go to 5 in my intermediate calculations, I'll be in good shape. Okay, so what's our temperature? Remembering our temperature has to be in Kelvin. So it's 6.33, so we can do that. 6.33 plus 273.15. Okay, so I could do that. It's tempting to do these things in your head, but I like to do the calculator every time just so I don't make an error. Okay, that's our temperature. Okay, and the volume was 10 liters. Okay, so now I think that we're ready to plug some numbers in. So the pressure of the N2O is our nRT on V. So we got 0.26130 moles times 0.0821 liters atmospheres per mole per degree Kelvin, times by our temperature, which was our 279.48 Kelvin, divided by our volume, which was our 10 liters. So moles, moles, Kelvin, Kelvin, liters, liters, and then that leaves me with the pressure of N2O. Only one thing left, atmospheres. So now I can put all of that into my calculator. So I'm going to use that answer from before. So times the temperature by the ideal gas constant times the number of moles of the gas. Enter, divide that by 10, enter, and I got, oh, see, it was almost exactly 0.6, right? 0.5996. So if I put that to 3 sig figs, it's going to be just 0.600 ATM, and that's the answer that I'm going to put in. All right, there we go. So now I've got to do the same for my SF4. Okay, So remember there are two compounds. One's called sulfur hexafluoride, which has 6 fluorines, and then there's this other one that is sulfur tetrafluoride, which has 4. So keep an eye on that because it's really easy to make that mistake. All right, so remember we're just working on the pressures at this point because that's really kind of like the big part of the question. So that's going to be 0.600. We need the trailing zeros to get our 3 sig figs. All right, this one's going to go a little quicker, but we will need the molar mass of the SF4. Okay, so the number of moles of SF4 was 19.5 grams, I think, but we'll just check that. See, no, it wasn't. That was the previous question. It was 17.8, yeah. 17.8 grams of SF4 times 1 mole of SF4, however many grams of SF4, right? So let's put that in. 108.06. Okay, there we go. So we're going to be well under a mole, right? Okay, so 17.8 times 1 on 108.06. Enter. There we go. 0.16472 moles. Okay, so there's that. All right. There we go. All right, so now we're ready to calculate our pressure of this gas. So remember, it's going to be nRT on V. So we just did our N, 0.16472 moles. Our R, 0.0821, that's the ideal gas constant. And then finally our temperature, which we calculated before. So it's a little quicker, this second one, isn't it? And we're going to divide it by a volume. It's still the same volume. It's 10 liters. So liters, liters, moles, moles, Kelvin, Kelvin. All we've got left is ATM. That makes sense because we're solving for a pressure. So go back to my calculator. Got my moles there. So I'm just going to take that answer, times it by the ideal gas constant, times by my temperature, divide by my volume, and bingo. And so I got 0.37796. That's out to 5 sig figs. And so then what I'm going to do is, for entering my answer, I'm going to round that to 3 sig figs. So that would be 0.378 ATM. Okay, there we go. All right, so I'll put that one in. .378. Okay, so it seems like we've got a heck of a lot to go, doesn't it? Right, now it's important that you show your work clearly for all of these things. The total pressure is just equal to the sum of our two partial pressures. And what I would recommend doing here is don't use the rounded off values. Use those values that we recorded to 5 digits and then round to 3 digits once you've done that. Okay, so I'm going to get the other one. It was like 0.5999, wasn't it? 0.5996. Okay? And so because we've got these extra digits in there, we're going to get, we're going to eliminate any of that potential rounding error. Might not be an issue, but it's always worth doing. So plus 0.5996, and that's going to give me the total pressure in ATM. So 0.9776 to, that's going to one extra digit. I'm rounding it off to the 3 digits, 0.978 ATM. So about 1 atmosphere, okay? So about 1 atmosphere, not too bad. All right, so that's the total pressure. Turned out that you could just straight up add those guys without introducing any rounding error, but we did it all legit. Okay, so now we've just got our mole fractions. So the thing about your mole fraction is this, right? Remember that the pressure of a component A is e to its mole fraction times by the total pressure. So let's just reorganize that formula. The pressure of A on the total pressure is going to give me my mole fraction. So these last two bits getting the mole fractions are going to be pretty simple. So the pressure, the mole fraction of N to O is just going to be the pressure of N to O over the pressure total. And similarly, the mole fraction of the other gas is just going to be the pressure of that gas over the pressure total. There we go. All right, so this one was 0.5996. We probably shouldn't work from memory like I just did there. You should probably always check everything. And then the other one was 0.9778, right? 6, see, little slips kicking in. And then we had, this one was 0.3 something, but we should look at what it really was, 0.37796. And 0.9776. All right, so just make sure you've got all those numbers correct. So that will be it. And the key thing to remember was your two mole fractions, they should always be numbers less than 1, but when you add the mole fractions together, they should add up to 1. So there's my total there. So this first one is pretty easy, 0.5996 divided by that previous answer, and I got a number less than 1, so 0.613. Remember, I can just round off at 3 sig figs because I'm not going to do anything more with this. This is my final calculation. And then finally 0.37796 divide 0.9776, enter, and then we go 0.387. And just double check those two should add together to give you 1. So 0.613 plus 0.387, 1. So I know I got it right. Okay, I know I got it right. Everything is internally consistent. Okay, that's a big question, and it's going to be worth a decent number of points. Because of that, it's important that you show your work clearly. You might not get everything correct, but most people are going to be able to get those partial pressures correct using the ideal gas law. Most people are going to be able to add the two together. Try not to make little numerical errors, and you'll do great. Okay, so we're still doing okay with our 10 minutes per question, and that one was a really hard one, so not too bad. All right, looks like this is going to be a qualitative question and a numerical question. So let's have a look here. It says, for many purposes, we can treat dimethyl ether as an ideal gas at temperatures above its boiling point. So this is going to be important. If the temperature is not greater than minus 24 degrees Celsius, it's not a gas. So at temperatures greater than minus 24 degrees Celsius, let's just do greater, this guy is a gas, all right? At temperatures less than minus 24 degrees Celsius, it is a liquid. And when it's a liquid, you can't use the ideal gas law to describe how it's behaving, okay? So that's an important thing. So it says, and this is when we're at like sort of normal atmospheric temperature pressures, right? So this would be like, at 1 atmosphere, at normal pressure, okay? So it says, suppose the pressure on a 560 milliliter sample, so they're giving you the volume here, right? That's the volume, of dimethyl ethyl gas at minus 5 degrees Celsius is reduced to 1/3 its initial value. Okay, so what we're saying here, so minus 5 is above minus 24, and we have some initial pressure, and then we drop it. so that we arrive at some final pressure, and that final pressure is equal to 1/3 of whatever the initial pressure was. So we made the pressure go down, okay? So what they want to say is it possible to change the temperature of the gas at the same time so that the volume doesn't change? Okay, so what we know is that PV equals nRT, all right? And so we've got some initial conditions, right? And then we're going to change it to some final conditions. And what we would like is for the final volume to equal the initial volume, okay? So, but the question is going to be, will the final temperature be less than the boiling point if we do that, right? Or will it turn into a liquid or something, right? That's the issue. So there's this thing called the combined gas law, and you can probably see this. So if I reorganize that first expression there, you can see that I would get a constant. It's called the ideal gas constant. And if I reorganize the second form of the ideal gas law there, you can see that I2 would get the same expression, be equal to R, which is a constant. So put that together, it really just means that that thing equals that thing, okay? So that's called your combined gas law. Now, it's a sample of gas trapped in a container, so we know that the initial number of moles is exactly the same as the final number of moles, so we can cancel those things out. We also have a situation where we want the final volume to be the same as the initial volume, so we can cancel those things out, okay? So now we are left with this. Now what we want to do is calculate that final volume there, right? We want to calculate that final volume. So let's kind of do that. So I'm going to bring the final volume over to that side and bring the pressure initial over to the right side, and then I'm going to bring the temperature initial up there. Okay, so it looks like that's it. And if I now go ahead and solve for the temperature final, I can see whether that is bigger than the boiling point, right? Now remember, I've got to work in Kelvin. So it looks like there's a bit of an issue here that we've got too many variables. Remember that the final pressure, P final, is 1/3 of P initial. So T final will be 1/3 of P initial, T initial over P initial, and then that'll cancel out, and you can see that we've just got the one variable left. So the final temperature is just going to be 1/3 of the initial temperature, and I think we started at, well, let's just double check, we started at -5, okay? So remember, we've got to work in Kelvin though. 1/3 of -5 plus 273.15. So let's do that. 1 on 3 parentheses -5 plus 273.15, close parentheses, enter, and that is 89.38 Kelvin. So our question is this bigger than the boiling point, right? Is that bigger than this -24 degrees Celsius? So now what I need to do is to go back into Celsius and compare it to that number. Now, it's not going to be, right? So 89.38 Kelvin minus 273.15 minus 273.15. Enter. You see it's going to be way lower. Well, that should be an 8, but it doesn't matter because it's going to be way lower than that boiling point. So if you try to do this process, it's going to turn into a liquid. It's not going to remain a gas. So you can't do it, right? So the answer is no, and we don't need a number in there. All right, pretty intense, but we're still doing our 10 minutes per question. It's going pretty good. All right, so this one, similar to what we had before, but with this one, we don't have to do the total pressure, right? Okay, now we might end up doing the total pressure, but I'm going to kind of tackle this problem in a slightly different way. So you have an 8-liter tank. This is its temperature, certain mass of sulfur hexafluoride. See how you've got to be careful there? And a certain mass of carbon dioxide. Both gases are going to obey the ideal gas law. We're going to calculate the mole fraction and partial pressure of each gas. In this case, we don't have to calculate the total pressure. So what I'm going to do is I'm going to just use these two formulas. The mole fraction of a given component is the moles of that component over the total moles. That's what I'm going to use to get my mole fractions. And then, to get the partial pressures, all I'm going to do is just use the ideal gas law. So PV equals nRT. We're solving for pressure. P equals nRT on V. And I'll have my different moles that go in there for each of those. So that's how I'm going to tackle it. So the temperature was 9.65 Celsius. That's going to in common. So we've got to convert that to Kelvin pretty quick. Always do that. For a gas law problem, you'll get some points just for converting your temperature to Kelvin. So 9.65 plus 273.15. Enter. There we go. 282.8 Kelvin. Always do that. Now we're going to go ahead and calculate the moles of each component. Do that. Make it really obvious and clear how you're doing that. Because, again, even if you can't solve the problem, you'll get some partial credit for that one. So the number of moles of SF6, not 4, right? So you want to be mindful of that. 17.4 grams of SF6 times 1 mole of SF6 has however many grams in it. We'll look that up in a moment. Moles, not grams. There we go. So we know we got that right. And then we've got to do the same with carbon dioxide. 6.41 grams. And it is 1 mole of carbon dioxide. And I'll speed this up a little bit. 44.01 grams of carbon dioxide. And that'll give me moles of that. Alright. So go over to our handy dandy calculator, SF6, 146.06. There we go. Okay, so plug that into my calculator. 17.4 times 1 on 146.06. Enter. And 0.11913, just carrying through a couple of extra digits, right? And I've got 6.41 times 1 on 44.01. Enter. There we are. 0.14565. Make that clear that that's a 4 there. There we go. Alright, so we look like we have everything we need to do our mole fraction now. So I'm going to go ahead and I'm going to calculate my total moles. So my previous answer plus 0.119129. go. So my total moles 0.2647778. Alright, so to get my mole fractions of my different components, so my mole fraction of SF6 is just going to be my moles of SF6 over my total moles, and that's it. Now sometimes people feel like, oh, I'm calculating a percentage here, I should times it by 100. You don't want to do that. It should always be a number less than 1. So 0.11913 divide second function answer, enter, and there we go, 0.450, and it doesn't have units because the moles cancels it. Alright, 3 sig figs on that guy. Alright, so now we're going to do the next one. When we do the next one, again, should be a number less than 1, and when we add the two together, they should add up to 1. So there we go. Alright, so 0.14565 divide 0.264778, enter, and to 3 sig figs this is going to be 0.550, and sure enough those two numbers add up to 1. So we do all the checks and balances there. Alright, so we got a whole bunch of problems there, right? We got a whole bunch of points there, so 0.450 and 0.550. Now calculating the partial pressure of each one is just going to be plug and chug in the ideal gas law. We kind of did the hard work with respect to calculating the moles of each of those things. So we've got our temperature in Kelvin, our volume is 8 liters, and we've got the number of moles of each component. We are good to go. So let's just do it over here. The pressure of SF6, it's nRT on V. Alright, and so pressure of SF6, our moles of that component was 0.11913. The ideal gas constant is 0.0821, and the temperature is 282.8 Kelvin. The volume was 8 liters, and that's it. Alright, now I didn't put all the units in. You should, you should do that because it's your test, right? You don't want to screw up your test. Now when I do this, the amount of the mole fraction of the carbon dioxide is greater than the mole fraction of the SF6. And so what that means for me is that the pressure of the carbon dioxide should be greater. All right, so keep that in mind as well. So I'm always very cautious to check everything, that I'm not like, copying a number over incorrectly. Sometimes people do all the work correctly on their pen and paper and then they copy the wrong stuff into Alex. So be aware of just taking your time copying those numbers over and questioning whether you've got everything correct. All right, you need to show your work clearly to be successful with this one. Okay, so pressure of CO2, same deal, nRT on V. There's our moles there, 0.14565. R is the ideal gas constant, 0.0821, and the temperature was 282.8. Our volume is 8 liters, okay? And that's going to be in ATM, and we're going to round to 3 significant figures. So same thing, 0.14565 times 0.0821. Oh, 0.0821 times 282.8. 8 divide 8. There we go. And remember, I'm looking for a number bigger than what I had before. It is. Alright, so that's perfect. Okay, so that's how I would tackle that one. And we're doing pretty good on time, so I'm happy about that. Alright, okay, moving on. Okay, hang on a second. Right, let's have a look at this one. So it says, Ancient Romans built often out of bricks and mortar. Okay, so they often built stuff out of bricks and mortar. A key ingredient in their mortar was quicklime, which is calcium oxide, which they produced by roasting limestone, which is calcium carbonate. So I want to get clear on this. Calcium is in group 2A, so it's 2+. Oxygen is in group 6A, so it's 2-. So calcium oxide is CaO. Okay, and then calcium carbonate, so again it's Ca2+, and then a carbonate anion is a polyatomic anion. Okay, so they're just going to be 1-to-1 as well. So I just want to get my two formulas straight. Write a balanced chemical equation including physical state symbols for the decomposition of solid calcium carbonate into solid calcium oxide and gaseous carbon dioxide. Okay, I can do that. So decomposition is just when one thing falls apart, and we're told that that's a solid, and it falls apart into calcium oxide, which we're told is a solid, and carbon dioxide, which we're told is a gas. So that's our kind of equation there. Now we just got to make sure that everything balances, and it actually looks really good because we've got one calcium on the left and one calcium on the right. We've got one carbon on the left and one carbon on the right. And then for oxygens, we've got 3 on the left, and then we've got 1 + 2, 3 on the right. So everything is just 1-to-1-to-1. So that's cool. Right? That makes it really easy. And I've just got to make sure that I put those physical state symbols in there. All right, we got that stuff. Now, so that's half my points. Yay. Or actually, it's probably one of the 3 points. And now it says, suppose 84 liters of carbon dioxide are produced by this gas. Of gas are produced by this reaction at a temperature of 260 degrees Celsius and a pressure of exactly 1 atm. Calculate the mass of calcium carbonate that must have reacted. Okay, so the key thing here is we've got a balanced equation. So I know from this that if I have the number of moles of carbon dioxide, that's going to be equal to the number of moles of calcium carbonate, and then I can just use the molar mass to turn that into grams, right? So that's the key thing about getting this balanced equation, is to realize that there's a 1-to-1 mole ratio between the carbon dioxide and the calcium carbonate. So now how am I going to get the number of moles of CO2? Well, CO2 is a gas, right? So we know that it obeys the ideal gas law. And you can see that if I do that, I can solve for the number of moles of the gas. So do I have the pressure? We were told it was 1. Do I have the volume? We were told it was 84 liters. Do I have the temperature? We were told it was 260 degrees Celsius. So this is going to be pretty straightforward. My pressure is 1 atm. My volume was 84 liters. The ideal gas constant is 0.0821 liters atm per mole per Kelvin. And then I just got to multiply it by the temperature in Kelvin, which is going to be 260 plus 273.15. Okay, and that's in Kelvin. So when I do that, my atm cancels, my liters cancel, liters, my kelvins cancel, and I'm left with 1 over moles, which is just moles. So this will give me my moles of CO2. Alright, so let's put all of that into my calculator. Having some window issues here. I want everything to tile and it's not wanting to do it. Alright, there we go. Alright, so we are 1, we didn't really need to do the 1, do we? Times 84, divide 1. All of this in parentheses are 0.0821, and then we want the temperature in Kelvin, so it's going to be 260 plus 273.15. Close all those parentheses off. There we go. And there's my moles of CO2. So it's 3.071. Okay, there we are. So, pretty happy with that. Now we also know that this means that there is 3.071 moles of my calcium carbonate. So all I got to do now to get my grams of calcium carbonate is multiply that by its molar mass. Upside down. So go over to my handy dandy molar mass calculator, CaCO3, and then we're going to calculate 100.09. And there we are. Alright, so pretty straightforward. Times 100.09, enter, and there it is. We need 307 grams of the calcium carbonate, and we know we got it right because the moles cancel that. So 307 grams of calcium carbonate. Alright, I'm pretty happy with that. So just double check that we got everything correct. 3 sig figs, units of grams, it all looks good to me. Alright, we got off there lightly because the mole ratio was all 1 to 1 to 1. Alright, this question is about ranking samples in terms of average kinetic energy of the atoms that are in them. So there's a little formula for the average kinetic energy, and so the average kinetic energy is just equal to 3 on 2 RT. So what we see here is that the kinetic energy just depends on one factor and one factor only, and that is the temperature. And so what it's really saying is that the kinetic energy goes up as the temperature goes up. So what's important to recognize is that amount is irrelevant. It doesn't appear in the formula. Pressure is irrelevant. It doesn't appear in the formula. It only depends on the temperature. So when it says rank these in order of increasing average kinetic energy, another way of saying this would be order these in terms of increasing temperature. That's it. So all you got to do is go to your lowest temperature, which is this one, that's a 1. Your next lowest temperature, that's a 2. Your next one, that's a 3. Your next one, that's a 4. And your next one, that's a 5. So often with these velocity and kinetic energy problems, they'll give you information that's not actually in the formula. You can just ignore that, and this is a classic example of that. Alright, so now we're on to calculating the root mean squared speed of atoms in a sample of gas at a particular temperature. So this is just going to be a plug and chug type thing, but we do need to remember the formula, right? So it's 3RT on M, but M is the molar mass, but it needs to be expressed in kilograms, right? So kilograms. M is the mass of an atom, but it needs to be in kilograms per mole, and then this guy here needs to be in Kelvin. And typically these speeds are of the order of hundreds of meters per second, so keep that in your mind. So let's go ahead and get the molar mass of this guy in kilograms. So it's xenon. So I'm just gonna go and look that up. Again, I got my handy dandy molecular weight calculator, but of course I can use it to quickly find the mass of an element, right? So just put that in and go calculate. You always want to hit calculate 131.29. So 131.29 grams per 1 mole. And we don't want grams, we want kilograms. So we got to remember that 1 kilogram is 10 to the 3 grams. And so this is going to be 0.13129 kilograms per 1 mole. All right, there we go. So that's for a whole mole of atoms, right? So if we just want to know the mass of one atom, how would we do that? So the mass of one, well, let's just leave, this is fine. Let's just leave that be. Okay, now we're going to do apply the formula. So when we apply the formula, R, the ideal gas constant, can be expressed in a couple of different ways. We can write it as 8.314 joules per mole per degree Kelvin, or we can write it as 0.0821 liters atmospheres per mole per degree Kelvin. Whenever we're dealing with something where we're calculating an energy or a velocity, it's almost always that we're going to work in that form. Okay, and when you apply the velocity formula, you want to be using this value. Otherwise, you'll get wackadoo numbers. Okay, so here we go. Let's just calculate this. It's going to be 3 times 8.314. And then we need our temperature in Kelvin. So this was minus 84 plus 273.15. And then we've got to divide all of that by the mass, the molar mass, expressed in kilograms per mole. So the root mean squared speed ends up being, let's do it, second function square root, clear that, didn't get the second function square root, there we go, 3, it's a little clunky with doing this on the keyboard, there we go, you can hear all my button presses. No. It's a little, like I said, it's a little awkward doing this on the computer. There we go. Oh my gosh. No real answer. I don't know, that is not, I must have a minus sign somewhere in there that there it is. There we go. I know what it is. I got these parentheses at the end there that I don't need. No! Don't do this to me. Alright, after all of that editing, we finally get there, and it ends up being 190 meters per second. which is a really reasonable answer, okay, because these are typically a couple of 100 meters per second. All right, guys, so that's about what we've got time for. So yeah, thanks for that, and I hope you found it helpful. And if there is time, I'll send out another video today where we look at the chapter 1 material. But I think if you look at the review for the other quizzes, you'll find that you've got what you need there to be successful on the test. Okay, take care, and yeah, have fun with everything.